So today we're going to get started playing around with using servo motors and some other sensors that are available to us to use with the Arduino or with any of the other similarly compatible microcontrollers that you may have gotten. So first up, let's talk about what a servo motor is. A servo motor is a type of motor, but it's different from several other types of motors that you may be familiar with. So there are our good old-fashioned DC motors that you might have seen inside of like one of those little fans that you might hold that like blows a very small amount of air on you. This kind of motor, a DC motor, can only it just spins. You put a voltage differential in between on these two wires, and this motor spins. There's also another kind of motor called a stepper motor. And there's various kinds of stepper motors in different shapes and sizes. But what differentiates a stepper motor from a standard DC motor is that a stepper motor operates in discrete steps. So this might be hard to hear. I'll hold it up to the microphone, but you might be able to hear this. Kind of makes a zh, zh, zh. So that is happening because the stepper motor moves in discrete little motions. So when you spin it quickly, you hear those motions. Or you hear each one of those little steps. And then that comes out as a little like zzz, zzz kind of noise. The benefit of using a stepper motor for robotics applications over a DC motor is the fact that you can have precision. DC motors, you just say, here's voltage, spin if you can, and there's no feedback system or a specific physical way to determine how far it's gone. So stepper motors don't actually have a feedback system, meaning there's no way to ask the servo motor what position it's currently in. But you can say, turn this specific amount, and if you've designed your system correctly, it will have spun that correct defined amount. But then that brings us to servo motors. And there's different kinds of servo motors. This is one of the cheapest kinds. But a servo motor is a combination of a couple things. The first thing that's in there is there is a DC motor. There's a regular DC motor that has a shaft that can spin. And attached to that shaft is a gear reduction. So there's a bunch of gears that make it so if this gear spins a bunch of times, it will be connected to another gear that will spin fewer times. So think about it, like if this tiny gear were to spin a bunch of times, because it's so small, its circumference might add up to only just a part of the circumference of this other gear. And on that shaft is another small gear that goes to a big gear, and then it might repeat a few times, so that when this DC motor spins many, many, many times, the output shaft spins much more slowly. So the output shaft spins slowly, while the input shaft connected to the actual motor spins very, very, very quickly. And this gear reduction does a couple things. One, it increases the power that the torque, the actual force that the motor can turn at on that output shaft, because it's sacrificing speed in favor of that torque, that ability to turn with more force. The other thing that it allows for is it allows for more precision. If you spin that DC motor a bunch of times, it's only going to move the output shaft a little bit. So you have time on your side for precision of how far you want the output shaft to actually turn, because you'll spin the DC motor for a longer amount of time with less actual change in that output. So we have a gear reduction. Let me just update my drawing here. We have a DC motor to a gear reduction to the output shaft. And then also on the output shaft, we have hooked up to this. So we have our DC motor. Let me see. We have our DC motor. Oops. Which spins fast. Spins fast. Oh, dang. Our output motor, which the shaft of which spins fast, the gear reduction causes the increases our power, or torque, I'll say, TORQUE, and decreases speed. And the output shaft spins slowly. And hooked up to this output shaft is, I'll just draw an arrow from that to a potentiometer. And so a potentiometer, if we remember, is essentially, and let me put that sideways actually so you can actually see it. Oh, is a knob. I mean, in the way that we normally interact with it. A potentiometer is a knob that we usually twist. If you have an amplifier or like an old school stereo system, or even like the volume on like an old car radio. Those are potentiometers, maybe. They might be another technology called a rotary encoder, but let's just talk about potentiometers. Potentiometers are used to change this rotational state into a measurable electrical phenomenon. So, just really quick before we get too deep down here, let's talk about what a potentiometer is. So if we remember, our potentiometer has 3 conductors coming out of it. I'll just draw that. So we have our 3 conductors coming out of it. When we use this, we're going to supply our positive voltage to one leg, one of the outer legs. The other side will be connected to ground. And that central leg is our signal pin. That means that this is the pin that's going to create our information about the rotational position of this. So the potentiometer translates angle to voltage, we'll say. And so what's happening physically inside of this, right? We have our 5 volts going in the case of the Arduino. And there is a resistive material. So this is our resistor. A resistive material, and then on the other side we're connected to ground. And the signal pin is connected to a little like hand of a clock kind of thing that can rotate and make contact anywhere along this resistive material. And so then it's going to be either closer, I'll just draw a couple positions of it. it's going to be either closer to the 5 volts or the ground, meaning there will be more voltage coming through this middle pin if the wiper is turned to be closer to the 5 volts, or less voltage if the wiper is turned to be closer to ground. So that's how we translate our angle of rotation of the knob on our potentiometer into voltage. Now take this thing here and shrink it way, way, way down and hook it up to a gear that is connected to our output shaft. So now, if we spin our DC motor a bunch of times, then our output shaft will turn slowly, which will in turn turn the knob of our potentiometer. And so then, by looking at what the output voltage on the signal pin of the potentiometer inside of the servo motor is, we can tell what our angle of rotation is. So yes, inside of this thing here is all of that good stuff. There is a DC motor, a gear reduction, and a potentiometer to let us know which angle we're rotated at. And you can hear the gears in there. I was holding that up to the microphone and spinning the what's called the horn of the potentiometer. If you spin that, you can hear the gears moving around. So that's the nitty-gritty of what's happening inside of the potentiometer. And now let's look at how we can use it. And once we get this thing hooked up to our Arduino, then we will take some time to working on controlling this with our physical interface. So back to this camera. If we have our potentiometer, let me zoom in. All right, so we have this potentiometer, and as you might notice, there are 3 wires coming out of this thing. A potentiometer generally has, or at least one of these hobby potentiometers has 3 wires coming out of it. One is the power, one is the ground, and one is the signal. Pretty common for this kind of component. So this particular servo motor is going to want, or it's rather designed to accept 5 volts on one pin, ground on another pin, and the signal. So we have, luckily, our little diagram here that tells us which pin is which. And if we take a second and look at the plug on the other end. Oh, come on. Yeah. You might be able to see that one of those is marked 1, and then it would be sequential 1, 2, 3. All right, so, ooh, that's an interesting little lens flare. Come on. So if we have the servo, that's focus. There we go. On this servo, we have black, white, and red. Red is going to be 5 volts. Black is going to be connected to ground, and white is going to be connected to our signal. So, what we're going to do now is first let's take our time and make this in our Tinkercad. So, going over here, I have my servo positioned in my workspace here. And if I take my mouse and I hover over any one of these pins, we can see them the labels come up: ground, power, and signal. They're in a different order than my servo. So pay attention to the colors. You'll probably have, you might have these colors, in which case it'll be the same. Black is ground, red is 5 volts, white is our signal. You might have brown, yellow, and red, in which case red will be 5 volts, brown will be ground, and yellow will be signal. And if anyone has anything else, pop it up in the chat and we can sort that out. All right, so continuing along, we have this servo here, and now, oops, we need to load up our Arduino, our microcontroller in this virtual circuit. So get into our search field, Arduino, and Arduino Uno R3 is comparable with what you most likely have gotten, unless you ended up getting a kit that has the Mega, which is a larger version that's a little bit more powerful, but essentially the same thing. So, what we're going to do now is we are going to, excuse me, we're going to hook this up. And I think, actually, I forget if this has the... Okay, so, yeah. So on Tinkercad, if you go to this button here that says Code, if we open that up, it's going to be first in this block code, but we're not going to use that. We're going to go to this drop-down menu and say Text. And we'll say Continue. And, yeah, I don't know that this one has... Ah, good, it does. Okay, so we can include our servo library. So there's this little button here that has our servo information. But if you are not working on here, this is good. Okay. So okay, so this line of code here, that is going to bring the servo library in. And so if we remember libraries, just like P5 is a library that extends the function of JavaScript, this servo library is a bit of code that extends the ability of our Arduino software to control these devices. Additionally, I'll open up the Arduino IDE as well, which hopefully we all have downloaded. And in the Arduino IDE, I can look at some example code. So if I go to File, Examples, and I scroll, I look down this list for the subheader that is library. The subheader that will bring us to the servo library examples. I will select sweep, first of all. And yeah, this is going to be the code that we're actually going to put onto the Arduino. We're not going to put the code on from Tinkercad. We're going to load the code onto the Arduino from the Arduino application. So I can close this little empty sketch. So I'm looking at this just because this is going to tell us where we're going to connect wires to actually hook this thing up to the Arduino board itself. So if we read through this code real quick, we can see here we have that line of code that's telling the Arduino to fetch that library from its libraries folder and include that when it's loading the code onto the board. We have a global variable that is a servo object, a servo data type, which is something that's included inside of the servo library. And the default name that we're assigning to that variable is myservo. And we have another global variable that's the position of the servo. And so these servos that you most likely have are they're 180 degree servos. They can rotate 180 degrees, 1/2 of a rotation. There are other servos that can only turn 90 degrees. There are servos that that are linear, where they don't actually turn, where they move out. There also is a kind of servo called a continuous rotation servo. Those are most likely not in the kit. They're not in the kit that I put together for class. They're not in the kit that I recommended for class. But if you do indeed have one, those work not by specifying the rotational position of the servo, but rather the speed that the servo should move at. So they're slightly different, just in case you happen to have one of those. But, excuse me, we will continue on as if we have, most likely, a 180-degree rotation servo. And so we'll just initialize that variable with a value of 0, so that we'll move our servo to one of the maximum rotational, like one of the ends of its rotational area. All right, and in the setup function here, we are attaching our servo using the attach method. So you remember we talked about methods being attached to classes or objects that are instances of a class. So my servo is an instance of the servo class, and that class has a method called attach, which is just telling the code that we're going to hook up our signal pin to pin 9. We'll hook up our servo signal pin both physically in the real world on camera here and also in Tinkercad. So going back to Tinkercad here, we can hook both of these up. I can take my ground and I can connect it to ground. I can take my power, I can connect it to 5 volts. I'm going to make that a little bit cleaner. I'll go like that so we can actually see the connection. And I'll take a second, I'll just change the color. Oh, they've changed this. I'll change the color there to be red and black. And I'll just move this so it's a little bit nicer looking. There we go. That's a little better. Okay, so we have our power and ground are connected. And now I'm going to connect the signal pin. And I'll just go the long way so you can actually see it. To pin 9. And I will make this one, I'll make it yellow so it stands out. Keeping in mind that in my particular servo, the signal wire on this is white, not yellow. So now we have our servo successfully wired in this demo, so we will now go over to the live real world version to do it there. So I have my Arduino plugged in, and let me zoom in again on this. Okay. Actually, I'll zoom out. That might be a little bit too close. Okay. So I have the Arduino here, and I have my servo here. And so because I can't just plug this in, I need to get out some jumper wires. So I have a few here. Let me see if I can get some nicely color-coded ones. I have a red one, a yellow one, and where is the black one? One moment, please. There we go. Okay, and a black wire. So now that I have my 3 jumper wires out, now I can connect these. So on here I have, I'll go black to black, and I'm using yellow for my signal wire, so I'll put yellow into my signal one, and red connected to red. So I know color is a little bit off on my camera, but you should be able to see that relatively okay. So now that I have that, I can connect them up. So if we recall, I want to connect my signal pin, or my signal wire, to pin 9. And that might be a little bit hard to see, but if we look closely, we can see that the pin is labeled right here, pin 9, and that corresponds right here to where my yellow wire is plugged in. And I can plug my black wire into ground. and my red wire into 5 volts. So there we go. If I rotate that a little bit, you might be able to see that those align there. So ground, 5 volts, and pin 9. And so I'll zoom out a little bit there so we can see the whole scene. All right. And there we go. I have my servo wired up to my Arduino. Oop. And now what we have to do is we need to load code onto there, right? We need to put our servo code onto our Arduino. So yeah, I don't remember if this has actually the example code on Tinkercad. So we'll just look at the actual Arduino software for this. So going back to our Arduino software, continuing through reading our code, we only got this far. In the loop function, which because this is C-based, not JavaScript-based, we define functions differently. Here we say void. But we have 2 for loops. So those for loops will continue running until the condition is no longer true, and then the code will move on. So that means that this for loop will loop 180 times, and then this for loop will move 180 times. Oh, sorry, this for loop will loop 180 times, which in turn will, each one of these, inside of that for loop, we are using the right method to change the rotational position of our servo. And we are passing in as a parameter this pause variable, position, which is being used in our for loop as our iterator. So our position will go from 0 to 180, and we will update the actual position of our actual servo. We have a delay, which is going to just stop the program from running for 15 milliseconds, and that's because that servo takes physical time to get between those locations. Remember, in the discussion of what the servo motor actually is, it's a gear motor, so it does slow the motion of it in favor of that increased torque. So we have to wait 15 milliseconds for the servo horn to actually move each time we update the position. And then we have another for loop in which we go from 180 to 0. You see the difference here. We have an increment there. We're adding 1 to the value of pause each time in this loop. And in this one, we are decrementing. We are subtracting 1 from the value of pause each time this loop loops. And then otherwise, the rest of the code in there is exactly the same. So with that, we don't have to write any code yet, but we will take this, and now we need to load it onto the board. So first thing we're going to do is we're going to go to our Tools menu, and we're going to make sure that our board is correct. So Arduino Uno is correct for what I have. If I go to the port menu item, now I need to make sure that I'm on the correct port. So Arduino Uno, select, and now we can upload the code. And I'm going to upload this, but I'm going to switch my camera over to the desk view first. Refocus a touch, and here we go. So you'll see some flashing lights, and then this servo should start jumping around. So it's uploading, the lights are flashing. And so now, if we look at this, our servo rotates 180 degrees-ish back and forth. So one thing to keep in mind with the cheaper servos, which are most likely the one that you have in your kit, sometimes they can't actually make it a full 180 degrees. So it might be wise to decrease this maximum number to, like, let's just say I'll go 170, and we'll make this one 10. Just because if you try to push the servo past its limit, like the physical limit of it, it can end up breaking the mechanisms inside. So sometimes, just to be safe, I will leave a little bit of a buffer on the edge. So I'll upload that one more time, and so now it'll spin slightly less. And actually, it doesn't look like it's spinning any less, which means, oh, that's because I didn't update this right here. Let's see about that. So it still looks pretty close to the same, but that means that we were indeed running into the physical maximum of how much this component can actually rotate when we were doing the 180 to 0 rotation. Okay, so now that we have our potentiometer, our servo motor hooked up, now it's time to control it with something. So to do that, we're going to first hook up a potentiometer, and we're going to use that to control the servo. So I'm just going to set that servo aside for a moment, and depending on what kit you got, your potentiometer may look like this, or it may look like this. Or there's another option of what it may look like. Let me see if I have one of those handy. 1 second, sorry. There's a third option of how it may look. I may have to open up this kit here. Ah, yes, there we go. Or it may look like that. And if you got one of the new kits, this part will be separate from the actual knob that you actually turn. So your potentiometer may look like any one of these things. So take a second and locate whichever one of these matches what you have in your kit. And I'll give you a minute or so to get that. And if there's anyone who is having trouble locating their potentiometer, just speak up and we can hopefully try to find it. It might be in like a little bag of stuff that looks like this if you got the kit off of Amazon. All right, so regardless of which one of these potentiometers you have, they're going to be probably most likely set up in a very similar manner, where the center pin on whichever one, magnet, is our signal pin, and the outer pins are our power and ground pins. So let's work in our simulated version first. So we will grab a potentiometer. Let's see, where do we go here? There we go. So I go back here, and I just clicked the code button so I could reveal the component library. And in here, I will remove the word Arduino, and I will search for potato or potentiometer. I'll just choose potentiometer. And I'll bring that right here. And if it makes more sense, what I can do is I can rotate these components. If I select the component by clicking on it, I can click this button in the top left to rotate it, just because that might be a little bit easier to see here. It might also pay now to include a breadboard. So we'll open up a breadboard component. And so now what we can do, I'm actually going to remove these wires, and we'll rewire this in the manner that we would if we were using a breadboard, which we will also update our physical setup to include. So I'm going to select my breadboard, and I'm going to actually rotate it so that it's in this nice, easy to read orientation. I'm going to take my 5-volt pin, and I'm going to connect it to my power rail, and I'll change the color of that wire to be red, get it nice and clean. And ground, I will connect to the ground rail, and I'll make that one black. And so now, if we recall, now our potentiometer, the entirety of this vertical line of pins, all of those are internally connected to our 5 volts. And similarly, in this vertical column, all of those holes, all of those pins are connected to ground. So what we can do now is we can move our our servo motor down. Actually, I'll just leave it over here. That's just fine. I will connect the, I'll connect ground to ground. 5 volts here to 5 volts. And I'll take a moment to just make that look nice. Turn that color to red there. And our signal pin, we will once again connect to, I'll just go right over to pin 9. And back to having that be yellow. And I'll update this IRL in a moment. And and now that we have that nicely sorted, the zoom on this is real touchy. We'll get our potentiometer in here. So actually, I'm going to rotate this to, to this position, because if we recall on our breadboard, all of these numbered rows, all of these numerical rows are connected to within that numbered row. Like so, all of this in row 1 is connected to every other pin in row 1, and every pin in row 2 is connected to every other pin in row 2. So we can take this potentiometer and plug it in so that each one of its pins is in its own numerical row. And we can connect one of these to 5 volts, and once again I'll keep my colors nice. One of them on the outer pin to ground, and we'll make that one black again. And our central pin, we're going to be connecting to one of the analog inputs on our Arduino. So I'll take that one, and we'll go connect that to A0. And this one, I'm going to make this one, we'll make it orange, so it looks different. And so now, if we look at this, we have still our servo connected just as it was before, but we have our ground, and our ground and 5 volts are connected to our power rail, so we have a lot more room available for our circuitry. So let's make this happen in the real world. I think it automatically saves, yeah. So I'll switch over to this camera here, zoom out, and we'll get started. So first up, I'm going to unplug the power and ground from my servo, my black and red wires. I'm going to bring my breadboard over, And now it's time to get some more wires. So I will get a black wire. I'll get an orange wire out for my potentiometer. And let's see here. Okay, so now I will connect a black and red wire to my power and ground, my 5 volts and ground. Red will go to my power rail. Black will go to my ground rail. And now I can take my black and red wires that are connected to my servo and just plug them in the same. Red into power, black into ground. And now, as you see, our servo is back in action. My potentiometer, I can hook up like so. If I have this kind, it can plug right in. And you might be able to see there, the pins coming into the board. And similarly, if I have this kind, it can also just pop right in. And this one is a little bit more difficult also because it takes up more room. So if you have this kind, what I would suggest you do is plug it in so that it jumps over this central channel. And so then instead of connecting to the pins all on the same side, you're going to have to connect 2 on this side and 1 on this side, or whichever orientation you have plugged it in. Because remember, there's no electrical connection in rows that crosses this central channel. This disconnects this side of the board from this side of the board. So for this one, I would have my signal pin plugged in somewhere in row 25 is where I plugged this in, so that it lines up right with the center. And then on the other side, if I was using this component, I would have my my black and red plugged in like that, so that they are lined up with those pins on that side. So that's how I would do it with this one. Sometimes these can be hard to pull out. If you have a little pair of pliers or something, that can be helpful. But so as to match my Tinkercad drawing, I'm going to use this big one. So if I plug that in, yeah. Okay, I think it's in. I have my central pin. I'm going to plug my signal wire into the same row. And my power and ground in to match. Right, you see how those line up with the pins behind? All right, and so now I can plug my power into the power rail, my ground into the ground rail, and my orange wire, which I think I have a longer one of, yes, into A0. And so now I have all of my physical wiring all done. So you might notice that this does not control anything. That's because we haven't included the code to make it control anything. Just get this stuff out of my way. So to control this, we need to do that with code. So we're going to remember that our job as programmers is to take an input and then through some sort of algorithmic encoding, turn that into an output. Or, I mean, that's a broad definition, but we're gonna do something in that black box between input and output to make something happen. So what we want to do is we want to have this potentiometer position influence the location that our servo motor is rotated to. So going back to Arduino, there's a couple things that we want to do. First of all is we want to let our Arduino know that we are going to use pin A0 as an output. So we'll say pin mode A0. Sorry, did I say output? I meant input if I said we're using it as an input. And this, we can find information on this here. If we go to the example, we can say examples, basics, analog read serial. If you need a refresher, the examples have a lot of stuff for you. So I'll just walk through this really quick. So well, they don't have the pin mode because you technically don't need to for the analog pins, but that's okay. It's good to see at least at this phase. So what we do is we are going to use the analog read function to determine how much voltage is making its way to the A0 pin. And in this example, it's displaying it to the serial monitor, which is here. Well, we haven't loaded the code, so we don't see anything. So first of all, let's just look at this example, and then we can apply what we've learned over into our active sketch. So I'll just load this up. My servo is going to stop moving because that's no longer included in the code that's on the board. But if I go to my serial monitor and I turn the knob, if I turn all the way one way, we get to 0. All the way the other way, we get up to 1023, right? And so we have this data right there that we have this range from 0 through 1023, and we need to turn that into data that goes between, we'll just go back to 0 and 180. I'll keep it at 10 and 170. Yeah, I think that's probably best. So if we have a range of 0 through 1023 in our knob and an output range of 10 through 170, what we're going to want to use is a map function. So I can just include that right here. We're going to take analog read A0 as our input, right? And our input range is 0 through 1023. Map works just the same. Well, pretty much just the same in Arduino as it does in P5. So that should be not too unfamiliar. So we have our input range of 0 through 1023, and we want to have an output range of between 10 and 170. And now let's load that code up. Look at our serial monitor. And now when I turn the knob, we have a range of between 10 and, if I turn all the way to the other side, 170. So that means that we now have manipulated our data range so that it's something useful to us. And now let's implement that. Let's make that move our servo. So we don't need to have the serial stuff for this right here. What we can do is we can just comment out these for loops, because we're not automating the motion anymore. Now we're just directly moving the servo. We're going to say we can say pos equals, and I can just grab this line of code that I just wrote where we're mapping our input from that analog pin to that other range. And then I say my servo, which is remember that's the instance of the servo object. We say my servo.write pos. So now, if we load that up, let's see here. Oh, I put a capital S, my bad there. Load that up. And now, if I turn this knob, it will move the servo to match what I do with my knob here. Oh, I see something maybe in the chat. Oh, okay. No worries if there was a disconnection. This is all being recorded, so I will post this up later. So now that we have our servo being controlled by this knob, now I want to try to use something that's a bit more exciting than this knob. What we're going to do is we're going to keep the code exactly the same as we have here in our example. But what we're going to do is we're going to replace this potentiometer with something else. So let me just first of all, I'll do it in the Tinkercad setup first. So what we're going to do is we're going to remove this potentiometer. Oops. And we're going to get another component. We'll start with the photoresistor. So the photoresistor is a resistor that changes its resistance value based on how much light is falling on it. So I'll just search for photoresistor and it comes up right here. And this works very similarly to the potentiometer, but what we need to do is we need to wire it slightly differently. What we're going to do is we are going to, I'll rotate the component so it lines up with our breadboard. One side is going to be attached to our 5 volts. The other side is going to be attached to our A0. And then that side that's attached to our A0 is also going to be connected to ground, but through a 10 kilo ohm resistor, a 10,000 ohm resistor, which is rather high resistance. But what it's going to allow, any charge to, any voltage to go to ground if it doesn't have an easier path through this this wire here. So, let me see here. So in our components here, we can search for a resistor. If I put it here, if I click on this resistor in Tinkercad circuits, you can see that I have a resistance value as an option here. So I'll say 10 kilo ohms, and we can see that the color code has changed here, where now it goes brown, black, orange, gold. And I've pulled one of those out of my kit as well. Yours, if you got the Elegoo kit, it will be blue, unless they've changed things. But there's a bag. Oh, sorry, that's the wrong camera. There's a bag of resistors that are blue, and on the little paper end piece, there will be one of them that says 10K, and that's the one that you will want. The color codes on the blue ones are very hard to read, so I wouldn't expect to try to look for brown, black, orange, gold, but just look for the one that's labeled 10K. All right. And maybe we'll pull, keep them at the ready. If we have time, we'll use another one as well. So with this, I'm going to put that so that it is plugged into the same row in this demo, row 2, the same row as one end of the photoresistor, one terminal of the photoresistor, the wire that goes to our A0 pin, and our resistor are all in that same row. And we're going to move our ground connection to the other side of the resistor. So if we were to trace the possible paths of our electricity, the electricity is going to, our 5 volts is going to start here, go through this wire into our ground, into our power rail, and it'll go through this wire into our photoresistor, and our photoresistor then can connect to, that voltage will either go through our wire here to our A0 pin, or it can go through our 10K resistor to ground. So let's now move over to the physical realm and do that ourselves. So I'm going to pull out my potentiometer, and now you can see that I'm not giving it any good data, so it's just gonna wiggle around because now it's just getting fluctuating static electricity. But what I'll do now, I will get my photoresistor plugged in to the same pins that I have, or let me zoom in, sorry. My photoresistor is plugged into the pins that my power and signal are plugged into. And now what I need to do is I need to bring my 10K resistor over, get it plugged into the same row as the other side of my photoresistor, and then I need to just move my ground connection over to match up with the other end of my resistor. And so now just make sure everything is plugged in nice and firmly. And now I'll zoom out again. Yeah. And now I have my light source here, and if I block that light source, let me get something that's good to block a light source with. I'll just use this thing. If I block the light, it turns. But it's not turning very much. And that's because the range of the data coming out of the photoresistor might not span. Oh, it's also a little loose in there. I might be getting a bad connection. The range of the resistance of our photoresistor is not necessarily the same as that of our potentiometer. So what we might want to do is go back over to our Arduino, look at our analog read serial sketch so that we can look at the numbers, right? Because we're using serial print, which is very similar to console log. What we're going to do is I'm going to remove this map first of all, so that we're just looking at the raw data from the analog pin. And I need to first upload this code. And now if I look at the sensor value, when I'm doing nothing, right, when I'm not interacting with the sensor at all, our maximum is around 870. If I switch back over here and I cover that, oh, what's going on here? Something may have shorted out. It goes down to, we'll just say about, if I cover it very completely, we'll just say 620. 620 to 870 is our range, we'll say. Right, so it's 870-ish here. If I cover it so it's blocking the light, we have, we'll just say, I'll say 630. Yeah, okay. So that means now I want to move back over to my code that I've been writing, and I'm going to change this range here because we're never getting down to 0. The lowest we're getting is 630, and the highest value we're ever getting out of this sensor was 870. So now I'll upload this code, and now so by blocking more or less light, now I'm controlling the servo. So as for the question about how this can be useful, right? Like think about like a like a plant. If you have a plant that needs more or less sun, you could have a light sensor on the plant and something that can move the plant closer or farther from your window, is one example. Or if you have a solar panel, this could be used to make a solar panel that tracks the sun as it moves across the sky to maximize how much power you're getting from your solar setup. Okay, so I think I want to try to get one more component in here, which is a button. So the buttons are a digital input, right? If I click it, it can either be, I'll hold it up to the mic so maybe you can hear the button happening. It's either clicked or not clicked. I'll let go, not clicked. It has two states, right? Versus the continuum that we have here, right? So that means if I'm going to hook up my button, I'm going to not be dealing with analog read as we are with our resistor here, but we're going to be dealing with digital read, right? Because digital is talking about binary, 0 or 1, aka true or false, or in this case, pressed or not pressed. So let's add a button in our example here. Let me just see if I can. Okay. Okay, so we'll go to our components here, and I'm going to say button. So if I have a button, the way that this works, this particular button, is it has 4 connections, right? 2 of which are always electrically connected, and the other 2 of which are always connected to one another. And then between those different sides, those 2 sides, when we press the button, it'll connect the circuit. So like if we made a drawing of what's happening inside of that button, we might see that we have our 4 connections. 2 of them are always connected to each other, and then inside there's a switch that can be broken or connected. Okay, so, and just to show that, I'll get my multimeter out. I think we might have done this already, but I'll do it again. I'll set my multimeter to, so it makes a noise if the connection is made. I think you can probably hear that. So if I take this and let me just get myself adjusted. So if I take my 2 leads and I touch them to 2 of these leads, that means that these 2, the leads that are on the same side, versus like how there's 2 sides of this that have no leads on them. The leads that are on the same side, those are the ones that are connected when I press the button, and leads that are on opposing sides are always connected. So that means that these 2, those are the ones that I'm interested in. Those are where my information can come from. So, let me just put that meter away. I'm going to, like I said, we'll first do this on the simulation version. So I'll bring this in, and I need to rotate this, right? Because if I put it in like this, that means that these 2 that are on the same side, they're in the same numerical row on my breadboard, which means they're already electrically connected. So when I press the button, nothing changes. I just have another connection on top of the pre-existing connection that is inside of the breadboard. So I have to take this button and I have to rotate it 90 degrees. And I'm going to make it span the gap just so I have more room to work with here. So I have this button. What I'm going to do is I'm going to take one side and connect it to power, and I will make that color red also. The other side here, I'm going to do the same thing that I did here. I want to connect the other side to ground through a 10K resistor. And this is just so that no like static electricity builds up. Just because the button is so close to, like those connections are so close, it can have an induced charge that can give false readings. So I'm just going to copy and paste that, get myself another 10K resistor, hook it up to the other side, and run a wire from that to ground, and I'll update the color of that lead as well. So now the electricity that's flowing through our button, well, right now there's no electricity flowing through because it's not being pressed. But if I were to press this button, then at this point all that would happen is there's a very resistive connection through this resistor, through this wire back to ground, because remember, we want our voltage always wants to get to ground. Now we want to connect our button to one of our digital pins over here. So we're going to do this same side that's connected to our resistor. We will make I'll try to make a relatively clean path here that doesn't get in the way of too much else, and I'll zoom out a little bit. Oy, oy, oy. Sorry, I got unconnected. And one second, I'm just gonna move my whole thing down. That was a little messy. All right. And I'm gonna connect to pin 2. And I will give this wire another color as well. I'll say purple. And remember, one thing to keep in mind, we don't want to plug into pins 0 and 1, because those pins, TX and RX, T for transmit, R for receive, these pins are used for basically the same, they're connected to stuff that's happening in the USB cable. So if we connect to those, it can mess with the board's ability to connect to the computer, and therefore stop us from being able to load code onto our board. So now that we've connected our button to pin 2, now when I press the button, if I press the button, that voltage can go through the button and then boing over and electrify pin 2. And then we can use a digital read to determine if there is voltage being applied to pin 2 or not. Yes or no. Okay. So now let's go back to the real world, and we'll duplicate that process really quick on our breadboard here. So I will take my button. I'm going to do the same thing. I'm going to have it jump the gap. And these buttons, you really have to jam them in there. You might have a smaller one that you might have to take a pair of pliers and like straighten out the legs of this a little bit so that it can actually get in there. But you really have to give it a pretty good firm press. So I get another 10K, a 10 kilo ohm resistor. And I can forego the wire. I can just jump straight from that row into the ground rail just to minimize the number of wire. I guess I'll just do it so it looks the same as the drawing, might as well. All right, so if I have my resistor there and my black wire going from that same row to the ground rail. Oh, one second. All right. Oh, I'm off camera, sorry. And the other side connected to the 5 volts on the power rail. And let me find a purple wire. All right, got it. And now in that same row that my resistor is plugged into, I connect my purple wire, and then that is going to go all the way over to pin 2 on the Arduino. And so now, once again, I can press this. Nothing is going to happen in my sketch because we haven't told anything to happen in our code yet. So let's just quickly hop back over to our Arduino code. And what we're going to do is now we will update this to include a pin mode for pin 2, so that we, once again, are telling our code to expect incoming data from there. So we'll say pin mode, pin 2 as an input. And we will, now we can just make a conditional structure. So let's make it so that our potentiometer responds, our servo responds to our photoresistor data unless the button is pressed, and then this will go to some set location. So that means that we'll say if, we'll make a conditional structure, we'll say if digital read 2 is high, high meaning has voltage, low is the alternative, meaning that there's no voltage being applied to pin 2. If digital read of pin 2 is high, then I need my curly brackets, and I will say my servo dot right, and we'll just say 90 degrees. So it's going to turn to 90. We'll say, let's make it 45 actually, so that it goes to a nice angle. So now, if I just run this, I'm going to comment out this code here, and let's just run that so we can see. Once again, I've capitalized the S without that I should not have done. And so now I press it, and it turned to an angle. There's nothing to make it go anywhere else, so we're just stuck here now. But when I pressed it, it did do something. So let's just re-upload the code and see if it does anything. So now I'll press the button, we'll see it move again. All right, so that's good. So now what we're going to do is, instead of just commenting this out, we are going to put this inside of an else statement that is, remember, an else that follows an if is, that code will be run if this condition is not true. So we'll say else go to wherever the data from our potentiometer, our photoresistor tells us to go. So let's load that code up. And so now it should respond to my hand unless I press the button. And now it no longer responds to my hand, but it rotates to a set position. All right, and I'll put this code, I'll update this code in the virtual version, just so you can see that. And so this, this isn't a very useful setup right here, but you can imagine, like, if this switch, instead of having it be a button like this, if, going back to the idea of this being like a control system for a solar panel, right? We don't want our solar panel to ever rotate, like, so that it winds up all of its wires and breaks itself, right? So that would be a case where we would use something like a limit switch, which is basically a button that if our solar panel rotates too far, it hits the button, and then it says, don't you dare turn any farther than that. So we would have a conditional structure that says, yeah, follow the sun unless you are hitting the end of your ability to rotate, and then don't go any further because it'll break. So that's just an example of how this kind of a system could be useful, where we have multiple inputs and a conditional structure that determines which one of those inputs is used to control our output.